Hello everyone, June the 8th. Alright, today's goal is to understand this. Okay, we've been struggling this for a few days and I have no idea. I tried to figure it out yesterday, but yeah. Alright, let's just do this one very fast. Count negative numbers in the matrix. Which is sorted in non-decreasing order, both row-wise and column-wise, the number of negative values. So non-increasing, so it always goes down. I mean, you can. Ooh, can you find an ON plus M? That is what we shall aim for, because OM times N is very easy, right? Okay, let's see. I think I've done this before. I don't remember, which is quite a shame. 4, 3, 2, minus 1. 3, 2, 1, minus 1. Minus 1, minus 2. Minus 1, minus 1, minus 2, minus 3. So non-decreasing both row-wise and column. So this and this are both non-decreasing. So what we can say is we can look for that's interesting. N plus M. How would you do N plus M? N plus M solution. Well, I mean, we know we can start from the right-hand side, right? I mean, this will definitely be the smallest, right? This one's definitely the smallest. So maybe we can start from there. And then what? And then we try to see this one. If this one is negative, then these two must be negative. Okay? And then what? Then we try this one. But this one's positive. Therefore, what if this one's positive? If this one is positive, if this one is positive, that means that actually doesn't mean anything. If it's all negative, that means like if a diagonal value is negative, or if any value is negative, right? If any value is negative, then that means everybody in this is going to be negative. That is true, right? So if anyone is negative, the whole thing is negative. Anyone negative, the whole thing is negative. Yeah, because it's smaller. So with that in mind, what can we do? We need to find we find negatives here. That means the whole thing is negative. And then we need to try to find, that does make a little sense, right? So if we find this one negative, then this whole column is negative, right? And then what? And then we try to find in this column, this is negative and the whole thing is negative. This column, and then this column. Is that? Yes, because each row we try to find, at each row we try to find a negative. Nah, not really each row. At each column we try to find. I mean, we can do each row as well. But if you do each row, is that n plus n? That's not n plus n. Because you have to go m. Hold on. Yeah, so if you go this way, you find the first negative, and then everything here is negative, right? Then you go one back, then you go down, because this is bigger than this, right? Then you go this position, then you go down, then you find another negative. And then you go to this position, then you go down, and then you go, I don't think so. How do we do n plus n? Something like that, right? Something like that. Yeah, we start from here. We start from this position. If it's positive, then we go down until we find a negative. Once we find a negative, then we know, because this is bigger than, like if we have a negative here, right? If this is the first negative, all of these are positive, all of these are positive. That means the next negative it will not be up higher, because this is positive, so everybody's positive. So when you need to search is starting from this, go to this position, right? Then you should go search, right? Find the first negative, and then you do this. Then you move here, right? Find the first negative, then you move here, find the first negative, and then you take. So with that in mind, we will do on to find the first one, on, right? And then we'll go down to get the first one, and then we will basically go this way, go to the left, and then go down, go to the left, go down, go to the left. So we will do 1 round, 2 round, and so it will be 2n plus m. Yeah, because this zigzag. Oh, we don't even need it. We just start from here. Down, zigzag. Yep, it's a zigzag. Gotcha. Well, it's take a while to figure out the zigzag stuff. Okay, let's zigzag this. Zigzag from top right to bottom left. Each time a negative is found, the rest of the column must all be negative. Then we move left, right? Then we move left and keep searching down and keep searching downwards. Okay, so how do we code this? I and j. Okay, ij equals hold on, we need to have mn equals len grid 0. Okay, ij equal to 0 and n minus 1, while I is larger equal to 0. No, I is smaller than m, and it's fine. And while I is this. Okay. While j is larger equal to 0. J is larger equal to 0. When say if grid ij is, count the number of negatives, larger equal to 0, then j, no. Oh, j is larger equal to 0. I is smaller than n, than m. If this is larger than I minus equal 1, right? Else break. Else we find a smaller, then we can update the result. Yeah, we say res plus equal to I m minus I, right? Yeah. And then j minus equal 1. And break. Else, that means we go through, then we just else we just break. Otherwise j minus equal 1, then we go back up again. Whatever the I is, we keep searching, right? If it's smaller than, we do this, then we search. And when we're done, then we return res. Let's see if this is correct. Lordy, out of range. Huh. That is interesting. Oh. I is m. No, I is 0. What are you doing? I is 0. I plus equal 1. That's 1. Got it wrong. Plus equal 1. Okay, give it a shot. Yep. That is, I think. Oh, I'm just curious. Just curious. For, let's say, v in row, v is smaller than 0, and we'll sum this thing. I bet it's not that slow. Hey, it's faster. But that's the way, I think. Let's see. Brute force. Binary search. Linear traversal. For row and grid, while current Is this right? This is the same thing, right? Ith row has the first negative element at index. Then the first negative for I plus 1th row can never be indices greater than x. Yeah. That's the same idea. I think it's the same idea. This is saying if this, the next one you have to go to the front to check. Mine is thinking about column-wise, but it's exactly the same thing. But I'm just full on using this. This is using the other one. Negative index is here, right? If it's this, we just keep going until we find something. Then we get this. Then I keep going on the next one. Yeah, that's exactly the same. But why does this look so much simpler? Because we can do it while I smaller than m and grid ij is larger or equal to 0, I plus equal 1. When it gets out, I say, right? That makes it look more similar. And then this is larger than 0, I plus equal 1 until we find something that's not, right? Then rest equals this, j move to the left. And then just keep going. And this will be right. Yeah. This is an update. Use better condition for the while loop. We can simplify the logic, the implementation a bit. I'll try this one. Now, I don't think it will really make things faster, but it would just be more interesting. Doesn't matter. Okay, so that's not... We need to figure out this. All right, let's just read. Okay, calm down, and let's just figure this out. Mark band position. Start a queue from a specified position. Add to the queue the following position from the current according to the rule from the condition. Go through all the queue to the end. Yes. At the beginning, we'll mark unvisited position as -1. So if position is not visited at the end, you have correct value. The initial position P, we mark it as 0. When we add any position to the queue, we get value from cousin position and increment by 1. So at the end, our visit array will be the result. And about how we get following position from the current, that's assume k equals 6. Right? So we have this, yes. So the starting position is position minus k plus 1. Well, it depends. Depends if we have enough. And next we get every position, even if we count from starting, not from 0, up to position plus k. Yes. Check edge case is 1. Yes. That's exactly what I did in this one, right? We add each position at most once to the queue, and we must check each position, so the problem in the way we find following position from the current one. The larger the window size, the greater its intersection for neighboring points, so we have the control positions that we have already checked. Here we saw all non-band positions in 2 arrays for even and odd positions. Whenever the position is used, we erase it from the array. Why do we do even and odd then? Non-band position in 2 arrays. Yeah, we can reduce the number of traversing, I guess. That's what we're trying to do. What is this list? This list is even or odd. How can you still visit it while you already eliminated? So basically what it's trying to say, what are you trying to say? What are you trying to say? We have all the positions. And then we have the start, the beginning and end. And then, given everything that's still available, we go through every one of them and we check. If it's, because we go right to left, it's larger than, if it is, and everything. So that's why we need to have a, that's why we need to have the beginning position, current minus k plus 1, an absolute value of this. The absolute value of this. That is an interesting idea. So this basically tells you the first possible position you can put. I mean, if the 1 is at the end, then yes. Hold on. This one I need to draw a little bit. So what you're saying is, if I am 1, 2, 3, 4, 5, 6, 7, 8. Now I'm just like, if my 1 is here, okay, so this is 0, 1, 2. Let's say the k is equal to 5. Then what you're telling me is 2 minus 5 plus 1. which is equal to -2. So you say 2 is the first position that we can put. Holy guacamole, that is correct. 2 is the first position you can put. Huh. How? So yes, we will, let's do 7. Okay. 7, this one will be -4, right? -2. So 0, 1, 2, 3, 4. So you say this is the first position that we're gonna get. 1, 2, 3, 4, 5, 6, 7. Holy guacamole. How? So you're supposed to go here. 0, -1, right? -1, -2, -3, and -4. You're supposed to go this 4 times. But in reality, instead of going this way, you just go 1, 2, 3, 4. 1, 2, 3, 4. Because we want to be, you know, so that's we're aiming this as the end. So we need to go 7 steps, right? 1, 2, 3, 4, 5. No, actually, not 7 steps. We need to go left. 7 minus 1 equals 6 steps. So the 1, 2, 3, 4, 5, 6, right? But after we go 2 steps, that means we either go further or we go this way. Oh my God. Ha. Then that becomes a beginning position. And your end position is, of course, this one plus. Right? We can plus. So we'll go 7 steps this way. 1, 2, 3. No, not 7 steps. We go this way, 7 minus 1 step. Right? We go this way, 7 minus 1 step. But then, when you know this position, what if we go beyond? That's a good question, right? What if we are here? Then we go beyond. So again, we'll go k minus 1 steps to the right. But 1, 2, after we go, you can call it n minus current. There's a number of steps left. Hold on. 3, 6. No. This is the number left. So after I go k minus 1. So hold on. Shall be the current, right, plus k minus 1. Right, that should be plus k minus 1. If we plus k minus 1, will be a position. But it also depends on how much we need to get. Yeah, this will end at a position. Right, will end at a position, but it might not be right because it might go too much, right? It might go too much. So what I want is the index, or how much it is. Because we go here and then we do this and then we just need to go backwards, right? Go backwards. And that basically is the remaining is n minus current minus 1 is the remaining minus this thing right? The remaining minus this thing is going to be the number of steps, number of additional steps. And then That doesn't look the same as this one. Hold on. Let's do the other way. Let's do the way that definitely works. Okay, so we'll have to move k, right? K minus 1. Let's say moving here, right? K minus 1, 2, 3, 4, 5. So k equals 5. We need to move 4. So what is this position? So this position is going to be, we can say the total minus this, right? What is this? This is the remaining, right? The remaining is n minus current minus 1. This is the remaining. Minus k minus 1. And then we say n minus 1 minus this thing. And if you expand inside, it's n minus current minus k. That's this, right? So this will work. And if we cut down here, then n minus current minus 1 is a small value. This is a large value, right? So we will do this, and then you will have to go back. So this is the amount it will go back. So n minus 1 minus the amount of go back, then you get, oh, this is, oh, just this thing itself is going to take effort. Okay, so we understood these two parts. And then another thing is, once we know the start, even if it's even, right? Let's say 4. If 0 is here, k equals 4, right? We can do the left. Well, the left is going to be this. The right is going to be, yeah, this is actually interesting. 0, 1, 2, 3, 4, 5. So will be 5. N is 1, 2, 3, 4, 5, 6, 7, right? N is 7. So 7 minus 5 minus 4 ABS of this, and 7 minus 1 minus this. This is 2 minus 2, so it's 2. So it'll be 4. 0, 1, 2, 3, 4. So this is the end. Is going to be here. Yes, it's always going to be. That's why we have even and odd. Gotcha. So now we'll just say every time we have the remaining size, because we want everything to be visited once. So when we visit it, we just discard it. We visit it, we discard it. Right? We visit and discard, visit and discard. I mean, we could have made this into a set, so it would be easier to discard. So each time we get smaller, Linked list, I'm not doing linked list, but I'm gonna try. Okay, so now I understood. To make it faster, the following solution is inspired by the basic idea is still BFS, but instead of looping through k, looping through the k-sized window for each element, we loop through the remaining unbound positions. That can be reached by the current node. And since for each node, the reachable positions must all be even indexed or odd indexed. We place the unbound positions in 2 sets. Each time a position is taken, we remove it from the set. Okay, rest is fine. This is fine. We'll say unbound. Unbound equals to 2 sets. Okay. Then we say what do we say? We'll go through n and everything. We'll put it in. Right? And if it's band, then we don't so we say band set equals band. Then for I in range, and if I is not equal to p, and I is not in band set, right? Unbound I mod 2 dot add I. So now I have the unbound. Oh, another very important trick is to find the index of the begin and end of the reachable positions from the current node. The trick is that if there are not enough positions to the left or right to extend a window, we can wrap back. We can wrap back via absolute value to obtain the real begin and end. So Q step, I mean everything is still right. This is not working. Oh my god, look at this. So Q steps. Okay, well Q for this. Now we can say low shall equal to a current position, right? Current position is I. Then we say I need to say k minus 1 minus I is the number of steps you need to go to the left, right? I mean, k minus 1 step is the number you need to go to the left from I. You need to go k minus 1, right? K minus 1. And the total number of steps that you have so far is I. So I need to minus, right, k minus 1 step. I need to minus k minus 1 step. If it hits at a certain position, then we're good. If it goes too much, right? So I minus this, then we write back. So we just go ABS. The leftmost position that can be reached. And high will equal to, so this is the same, we start from I. We need to find the rightmost that we can reach, right? how much we can reach to the right. So it will be the remaining. Right? What's the remaining? The remaining is whatever we have, n minus 1 minus I. This is the remaining positions. So we can go. Then minus k minus 1. Right? Minus k minus 1. This will be whatever we have left. Then we need to go from here, from n, to go back that many times. Right? So which means if this is a positive value, okay? If this is a positive value, let me think again. N minus 1 minus I. Yeah, n minus 1, 3 is just how many we have left. So among this, we need to minus the number of steps we need to take. Then we have the remaining, right? We have the remaining. If it's 1, so we say n, need to minus this. N need to minus this. But what if n minus 1 minus I is too small? And this is bigger, right? If it's bigger, then we're just starting from here and then go back. Hold on, I got a little bit confused again. About this position, right? If we go to the right, fk if is 7, right? Then we need to go how many steps? I'm gonna go 1. It has 1 here, right? What is this 1? It's a 1, 2, 3, 4, 5, 6, 7. So 7 minus, right? 0, 1, 2, 3, 4, 5 minus 5 minus 1 is how many steps we have left, right? And then I need to go 4 minus 1 here. This is the number of left. This is the number we need to go to the left, right? If I have something remaining, then that means this is the amount of steps we need to take. So it shall be, so this will be 1 minus 3 will be 2, right? So we need to take 2 steps back, which means in here I need to take 3 steps. 1, 2, 3. But those 2 steps I cannot take. I started from this position, now I need to go back 2 steps. So that's gonna be 7 minus 1 minus this. But what if I don't? What if I have enough? Then that just means we have total number, right? Now we this total number we can go, then we minus 1, 2, 3. Right, minus this. We take those 3. Okay, we take those 3. And this is the whatever is left. Then we should start from here and take this much. Yes, now that makes sense. So yes, so it's going to be n minus 1 is the number left, right? N minus 1 minus this is the number of positions we can move. K minus 1 is the number we need to move. And ABS this is the total number, right? ABS this is the total number that that we can move. So it's either going more to the right or you have to double back. So if you double back, then you have to minus 1. So this is the rightmost position that can be reached, right? So now we have a low and a high. So instead of doing this, we don't do it this way. So instead of traversing the entire window of size k, we go through whatever unbound set we have at the moment, right? We go through whatever unbound set at the moment. If the node in the unbound set is within our range, low to high, we can include it in the next queue, in the next round. And we also delete it to reduce the size of the unbound set once. Yes, that's how you go through each node only once. So we have to change this, okay? So we need to first know which thing are we doing, right? Which thing are we doing? So we can say unbound, current unbound shall equal to, we have to turn into a list because we cannot traverse a set while we're changing the set's size. So we need to get this low. This is the current unbound. Of course, I'm going to turn that into a list. Okay. Then we go through this. So for j in current unbound, right? So we say if low is smaller or equal to j, smaller or equal to high, right? It's within. We can sort this. I see what you do there. You can sort it. If you sort, hold on. Oh no, that's not going to help. Let's just try if we don't sort, okay? Let's just don't sort it. Maybe it does help sorting. What do you think? If we sort, the first thing we start, and then if it gets smaller, then we don't do it anymore. Otherwise, we have to go through the entire thing. And then we have to go through the next round and go through the entire thing. Smaller, right? The entire thing. Let's now, but we already do the, maybe. Let's go sorted. Okay? We can even say sorted and reverse. It doesn't really matter. So we can say, yes, for j in this case, we can probably do this. Unsorted, okay? So if low is, if j is smaller than low, if j is, if low is smaller equal to j, smaller equal to high, okay? If that's the case, okay, this is the unbound, then we need to get it, Okay, we'll get it by saying rest j equals to this, temp add, and unbound this will dot remove j. Okay, so we go again, we go again, we go again until it gets bigger than high, right? We say elif j is larger than high. That's when we break. We don't have to keep going. J is already larger than it. So we do all this. Once we're done, we do this and this, and eventually return. All right, let's give this a shot. It passes this. It passes everything. Holy moly. Oh. Come on, let's try this one, right? The really, really nasty one. Okay, let's see. Ooh, it's still slow. 535. I think it's better than what we had in the past. Huh. Not enough. Not enough. This is not enough. I mean, what do you think? We can try, like, don't sort it, then just go through the entire thing. Okay, don't sort and go through the entire thing. Is this the same as this one? 1005 2865. Yeah. No, hold on. This is a different one. 696. 696. How many do we have this? 694. Only get 2 more. Damn it. Doesn't look. Oh no. Oh no. Nope. This ain't gonna work. Okay, so I have to keep going. My. Linked list. Yeah, I don't want to do a linked list. Alright, so we have to go for the ultimate kill. Unfortunately, this one still TLE because using a set is still not the best, right? Option. All right, I'll stop right here because I leave this final thing to tomorrow. We can read it and I can try to think about it tonight during sleep. Like, what is this binary search tree actually doing? Binary search tree. Binary search tree. I mean, this whole thing is sorted, right? If I do this, sorted, okay? Are you saying we need to do a balanced binary search tree where we will also erase node and maintain the balance? Yeah. Basically, what you're saying is when you try to search, how do you try to search? Because it searches one by one. How do you search here? Yeah, we'll deal with a tree later. Tree.find beginning. Oh, that's how you use. That's how you use sorted list. Yeah, sorted list. You can very fast define from begin to end, or from low to high, which one are in them, and you can remove them. So we'll find this. Yes, that will be take a log. This is log n, right? This is log n. Now we find it, and then we'll just traverse it. Tree.erase. When you erase, you return the next one? You gotta be kidding me. How would you maintain a balanced tree? Okay, this is something I have to learn again. Balanced binary search tree. Is this AVL tree? A self-balanced tree. Is this what we have to do? Damn. Oh my goodness. Nope. Mm-mm. That is way... They have to rotate. What the hell? Self-balancing. Is this self-balancing? What is this? Actually, I never really get into this. Let's see, what's the implementation of this? If it's easy, I might just take a look. Wait, where's the algorithm? My God, it has rotation as well. All right, this is going to take a lot of effort. Jesus Christ. All right, pick one. Pick one. You gotta do one. We can't just leave it like this. Okay, I picked this. I pick AVL tree then. We will. Okay, we will figure it out. I mean, we figured it out in the past. It's just it's been too long. I just forgot. Yeah. This is better. This is not as bad. You might be able to memorize how this one's done. Oh God. Oh no, this is just insert. Wait, we still have the delete to do. Oh my God. Delete. Insert. Delete. Here we go. A root of the modified subtree. Is that the next one? Man, there's a lot. There's a lot going on. All right. I think now I can. This is just a erase. Because I think this erase is special. They definitely. Anyway, this is a good approach. We can do sorted list. I range. What the heck is I range? I think sorted list is based on what? Is this is a is it red, black, and tree for the sorted list? I remember I read it somewhere. I don't. Anyway, we need to see the. Can I search? I range. What's this I range? Between minimum and maximum. gets everything out. Holy crap. Okay, do we have sorted list? Yes, we do. Solution 3. Using sorted list to quickly pick out all the unbound values from low to high. If we want to do this from scratch, we need to implement a self-balanced binary tree. Yet, sorted list is a shortcut. So we need to say import sorted containers. Okay, so this is gonna be sorted containers dot sorted list, and this will be the same. Okay. Is it append or .add? Okay, da. So this can be iRange. Discard. I think everything is log n, right? Update. Okay, log n. Discard is log n. Yeah, this must be a balanced. It's a balanced tree. iRange. So for j in dot iRange low to high. Oh, we need to inclusive. Oh, all inclusive. Okay. Is an iterator. So we do this. Okay. Say this of stuff, this does. And remove. Can we remove it? We can. Let's see, this is right. Index out of range. Out of wait, hold on. It has to be in range. Hold on. Let's say C to H. Oh, H is in L. Yeah, it should be fine. I would just get everything. Hold on, but why? In this case, it says it's the last one, right? List index out of range. Which list? I get 2. Oh, because you're removing at the same time. Dude, how am I supposed to not? Oh, you list it. Got it. List it. Yeah, that makes more sense. There you go. Yep. Oh, it's almost exactly the same. Yeah, I have no idea why I don't do it earlier. Oh, that's so much faster, huh? But we will implement binary search tree. You can't just let it go. Okay. Sorted list definitely is good. But yeah, here we go. We'll do this. Insertion. Okay, that'll be it for today. We have good. We understood. All right, we understood. We know what we're trying to do. We know the range. Basically, we're just saying how do we pick out values in a range from a sorted list? And the answer is sorted binary search tree, self-balancing binary search tree. Okay. Yep, we'll do this again tomorrow.